When you think about our digital world, it's kind of mind-blowing. Everything from the OS on your phone, your computer, even tiny chips and everyday gadgets. So much of it rests on this hidden foundation. And often that foundation, it's C, the C programming language. It's just everywhere, really shaping the bedrock of computing, even if we don't see it directly. Welcome to the deep dive. Today we're aiming for a shortcut, really, to understanding what it means to master C. We're pulling insights from a really excellent guide, Effective C, An Introduction to Professional C Programming by Robert C. Seacord. It came out from No Starch Press in 2020, and look, this isn't a book for absolute beginners. It's really aimed at developers who, already know how to program but want to get to that professional C level.
Yeah, and Robert C. Seacord, he's perfectly positioned for this. He's a technical director at NCC Group, known for secure coding training, not just in C, but across languages. And what's really telling is his role on the International Standardization Group for C itself, WG14. Plus, if you're into secure coding, you've probably seen his name on the Cert C coding standard. He really knows his stuff.
Right. So our mission here in this deep dive, it's ambitious. We want to pull out those key insights, those essential nuggets that help you write C code that's robust, portable, and crucially secure. We'll dig into some maybe surprising facts, some best practices that show how C really does strengthen computing's foundation. It's not just about knowing C syntax, it's about writing effective C. Ready to jump in? Let's start right at square one. The classic first program. Hello world. You know the drill. Hashtag includes studio.h, hashtag includes sitelib.h, then int main void, return exit success, and verge. Seems utterly basic, right? Foolproof, almost. The Seacord points out right away that even this simple thing teaches a fundamental C lesson. What's that hidden discipline?
It really comes down to responsibility, even for the simplest task. That puts function, it just prints stuff, but it can fail. It actually returns EOF, which is a negative integer, if there's a write error.
Well,
Now, maybe it's rare for standard output, sure, but think about writing to a file, maybe a full disk or a broken network pipe. Very possible.
so C is basically saying don't just assume things worked, verify. The book shows this improved version. If puts hello world, EOF, return exit failure, help return exit success, and boom, right there, you've got a core C practice. Check return values, always. Signal success with exit success, which is 0, or failure with the exit failure, non-zero. It's a mindset.
Exactly. That proactive error checking, it's fundamental to C's nature because it's low level. You, the programmer, are explicitly responsible for these details. When you declare a variable, you give it a precise type and identifier. It's not just good form. It's how the compiler understands memory allocation, data interpretation. And the C standard, currently C17, that's the final word on how the language behaves.
And that standard gives compilers, the implementations, quite a bit of latitude, doesn't it? That flexibility lets them be super efficient on different hardware. But what I find fascinating was the book's claim that basically no real-world C program is strictly conforming for maximum portability. Is that really the case? How do you balance that portability need with, getting things done?
Oh, absolutely true. Strictly conforming means you follow every rule, rely on no implementation defined or undefined behavior. In reality, almost every program uses something non-portable. Maybe it talks to specific hardware, uses a compiler extension. The key isn't avoiding it entirely, but being aware of where you deviate, documenting it. Conforming programs can use non-portable features. They just understand the trade-off.
Okay, so we've got data defined precisely. How do we actually manipulate it effectively? This inevitably leads us to pointers. C superpower? Maybe, or its biggest headache.
Both, probably. Fundamentally, pointers are just variables.
Right.
But they store memory addresses. They're how C gives you that direct, raw access to memory. And why are they essential? Well, think about the classic swap function example.
Right, the one everyone struggles with at first.
If you try to write void swap, int A, int B, just passing the integers,
It doesn't work.
it fails because C is passed by value. The function gets copies of A and B, not the originals.
So swapping the copies inside the function does nothing to the variables outside.
Okay.
The book shows the correct way. Void swap int pa, int bb,
Yeah,
using pointers.
exactly. P and PB are pointers to integers. You call it with the address of operator in kind A, like swapping A to B. Inside, you use the dereference operator, the star mera, to get to the values at those addresses. That swaps the originals. And this difference really highlights storage duration too. Automatic for local stack variables versus allocated for dynamic heap memory.
C also uses scope to control where names are visible, right?
4 kinds: file block, function prototype, and function scope. Like declare something outside any function, it gets file scope visible in that whole .c file. Understanding scope helps avoid naming clashes, makes code clear.
And building on basic types, we have derived types. Arrays, for instance, contiguous sequences, and typedef. That lets you create an alias, like typedef unsigned int type. But the book gives a specific warning about typedef names, something about T.
Yes. Avoid ending your own typedef names with T, that suffix, and related ones like intxt, dantxt, are reserved by the C standard and POC for their library types.
So if you use it, you might clash with a future standard library type.
Exactly. Could cause weird compilation errors down the line. Small detail, big impact on portability.
Then we have structures, structs, grouping related data. You access members with a dot, or a if you have a pointer to the struct.
And unions. Similar idea, but all members share the same memory space. They overlap.
Clever for saving memory, right. Store an int or a float, but not both at once.
Precisely.
And finally, type qualifiers. Adding nuance. Const is pretty clear, makes an object read-only.
Right. Attempting to write causes an error, and the compiler might even place it in read-only memory. Good for security.
Then volatile. This one seems trickier. It tells the compiler what exactly?
It tells the compiler, hands off. Basically, don't optimize away reads or writes to this variable, because its value might change unexpectedly from outside the program's direct control. Think hardware registers or maybe signal handlers. But, and this is critical, volatile is not for thread synchronization in C. That's a common mistake. You know, proper atomic operations or mutexes for that.
That clears up volatile a lot. Okay, and then there's restrict. This sounds powerful but subtle. It's a promise you make to the compiler about a pointer.
Yes, a promise. You're saying, for the scope of this pointer, it's the only way this specific chunk of memory will be accessed.
And if the compiler believes that promise,
it can optimize much more aggressively. Reorder operations, cache values, avoid redundant memory reads it thinks might have been changed through another pointer.
But if you break the promise, if another pointer does access that memory,
undefined behavior, crashes, corrupted data, logic errors that are incredibly hard to debug because the optimization obscures the cause. So use restrict carefully only when you're certain. And since C11, there's also atomic concurrent stuff, guaranteeing atomic operations for thread safety.
Okay, we've seen how C demands care with memory, but even simple numbers like integers have quirks. Integers come in signed and unsigned flavors. What's the key difference again?
Signed can hold positive, negative, and 0. Unsigned holds only 0 and positives. The crucial thing is knowing their limits, defined in limits.h. Unlike some languages that might throw an error on overflow, C integers have fixed sizes. And what happens at those limits, especially for unsigned types, can be surprising.
Surprising is one word for it. This unsigned integer wraparound seems like a classic C trap. Incrementing the maximum unsigned int uint max wraps around to 0.
Correct. And decrementing 0 wraps around to uinips. No error, just wraparound.
And this isn't just theoretical. It causes real bugs. Can you give an example?
Sure. A common one is a loop, like for unsigned int I, some value, I hit 0 and I. Someone used to signed ints expects it to stop when it hits 0.
But it's unsigned. It can never be less than 0.
Right. When it decrements from 0, it wraps to uint max. Infinite loop.
Ouch.
Another is checking if ij0 with unsigned I and j. That condition is always false. Subtraction result wraps around. It's never negative.
So you need to check if ji instead.
Exactly. You have to be really precise with unsigned arithmetic and comparisons.
Okay, moving from data types to controlling program flow. We have expressions and operators. There's this distinction between value computations, just calculating result, and side effects.
Yeah, side effects are actions that change the program state. Modifying a variable, doing I/O, calling a function that does those things.
This ties in something subtle. Order of evaluation and sequence points.
Right. Operator precedence tells you how A plus BC groups, but it doesn't always say if A is fetched before B. The book's example is max. G, you don't know if F runs before G or vice versa.
And if those functions have side effects, the result could change depending on the order.
Precisely. The order is often unspecified.
That seems dangerous. So how do you guarantee order when you need it?
You introduce sequence points explicitly, like assigning results to temporary variables first. Int feeble f. Int voice is int max value, int max values, max feeble. Now, f definitely finishes before g starts.
Got it. And speaking of assumptions, there's Knuth's famous quote, "Premature optimization is the root of all evil." The book brings this up with bitwise shift operators, and why not use them for fast multiplication or division by 2?
Well, you can, but it's usually better to just use the normal arithmetic operators, and these tectonic compilers are smart. If a shift is genuinely faster on the target shift for multiplying by 2, the compiler will probably make that optimization itself from your 2 code.
So using shifts directly is premature optimization.
Often, yes. It makes the code less clear, potentially introduces bugs if you get the shift wrong,
Yeah.
especially with signed numbers. Write clearly first, use arithmetic operators, profile later if needed, then optimize bottlenecks, trust the compiler.
Makes sense. Then logical operators in A&D and OR, they do short circuiting. How is that useful?
It's incredibly useful. It prevents unnecessary work or errors. Take PRNN PTR equals N. If PTR is NOL, the first part, PTR, is false. Because it's N and the whole thing must be false. So the second part, PTR equals N, is never even evaluated.
Preventing a null pointer crash. Elegant.
Exactly. Or is fill a ready prepare file. If the file is ready, the potentially slow prepare file function doesn't need to run.
Okay, beyond expressions, we have if-and switch for decisions. Switch needs care with default cases and avoiding fall-through, though warnings help. Then loops, .while, do, .while. The big danger is infinite loops, right? Making sure the condition eventually becomes false.
Absolutely. Got ensure termination. And then there's goto, the statement everyone loves to hate.
Yeah, it has a terrible reputation. Spaghetti code.
It does. And often, heavy goto use is a sign of poor structure. However, the book argues, and provides examples like the Linux kernel, that goto can be used in a disciplined way, specifically for error handling and resource cleanup in complex functions.
Like jumping to a cleanup section at the end.
Precisely. The copy process function in Linux apparently uses 17 goto labels for exactly this kind of structured exit path, ensuring everything is freed correctly no matter where it fails. So not always evil, just often misused. And of course you have continue and break for more localized loop control.
All right, let's switch to memory management. Dynamic memory. Allocated from the heap at runtime, we use malloc to get memory, realloc to resize it, free to give it back, but realloc, that one has a notorious trap. What's the danger?
The danger is when realloc fails. Maybe there isn't enough contiguous memory for the new size. If it fails, it returns NUL. But crucially, the original memory block you passed in is not freed.
Ah, so if you do P equals realloc, new size, and it returns NUL.
You've just overwritten your only pointer P with NLL, losing the handle to the original memory. Instant memory leak, and you lost your data.
Ouch. So what's the safe way to use realloc?
Use a temporary pointer.
Yeah.
Temp realloc key, new size. Then check. If temp, L is NUL, handle error, maybe free po P, only assign back to P if the allocation succeeded.
That makes sense. The book also mentions realloc array.
Yeah, it's a safer version for when you're calculating the new size by multiplication, like count element size. It checks for integer overflow in that multiplication, which could otherwise lead to allocating too little memory.
And when you're finally done with heap memory, you must haul free. But there's this best practice. After freeing, immediately set the pointer to NLL, free. PDR, PDIR, NELL equals NULL. Why that extra step?
It prevents double free bugs and use after free bugs. Freeing an NLL pointer is harmless, a defined no-op in C. If you don't null out the pointer after freeing, it becomes a dangling pointer. It still holds the address of memory you no longer own. If you accidentally free it again later, crash, or worse, if you use it after, it might have been reallocated. Undefined behavior, potential security hole.
So nulling it makes accidental second freeze safe, and accidental uses likely crash immediately, which is easier to debug.
Exactly. It turns a potential vulnerability into a predictable crash or a no-op.
What about variable length arrays, VLAs?
Okay.
From C99, arrays sized at runtime.
Right. They seem convenient. They're typically allocated on the stack, like local variables, and automatically freed when the function exits. Similar to Elica.
But they have downsides. The book seemed wary.
Big downsides, yes. The main one is stack overflow risk. The stack is usually much smaller than the heap. A large VLA, especially in a recursive function, can easily exhaust the stack space. And there's no standard portable way to check how much stack space is left before allocating a VLA.
So it's unpredictable, potentially dangerous.
Very. That's why they're often banned in safety-critical systems, avionics, medical devices, etc. The risk of sudden stack overflow is just too high.
Let's talk characters and strings. C started with ASCII, right? 7-bit, very US-centric.
Fine for basic English, but not the world.
So we needed Unicode, and C introduced rich-chart for wide characters.
Right, and Unicode has different ways to be encoded. UTF-8, UTF-16, UTF-32. UTF-8 is hugely dominant now, especially on Linux and Mac OS.
Why UTF-8? What's its advantage?
T-advantage. ASCII compatibility. The first 128 characters are identical. So much existing C code just worked. Plus its variable width. Uses 1 to 4 bytes per character. often more space efficient than fixed width like UTF-32, particularly for text heavy on ASCII characters.
But Ratchart itself has a portability problem. Its size varies.
Yes, big time. On Windows, Ratchart is usually 16 bits. Good for UTF-16's common characters, but characters outside the basic multilingual plane need two processors, a surrogate pair. On most POS systems, Linux, Mac OS Ratchart is 32 bits. It can hold any Unicode character directly, UTF-32.
So code using Ratchart might behave differently, or even lose data, when moved between Windows and Linux.
Absolutely. Handling Ratchart portably requires careful attention to the underlying encoding and potential size differences.
And fundamentally, C doesn't have a built-in string type, does it?
Nope. C strings are just arrays of characters with a special null character, 0, marking the end.
Which leads to the crucial difference between string size, the allocated memory, and string length characters before the null.
Exactly. And misunderstanding this is where many bugs originate.
Which brings us to the function hall of shame, gets. Why gets universally condemned?
Because it's inherently fatally flawed. Gets reads characters from input until it hits a new line, or EOF. Crucially, it has no idea how big the character array, the buffer you gave it, actually is.
So if the input is longer than the buffer,
It just keeps writing.
Yeah.
It's the end of the buffer, overwriting whatever happens to be next in memory.
that's a buffer overflow, the classic C vulnerability.
The classic. Leads to crashes, data corruption, and potentially allows attackers to inject and run their own code. It's so bad it was officially removed from the language standard in C11. Don't use it. Ever.
Okay, so the fix is functions that do know the buffer size, bounds checking interfaces.
Yes, like the optional S secure functions added in C11 Annex K, such as gets. These functions take an extra argument, the size of the destination buffer. They perform runtime constraint checks. If a check fails, like trying to write past the buffer, they're supposed to detect it and call a special handler.
And that handler can be set to log, abort, or maybe even ignore it, though ignoring is risky.
Right. The key point, though, is you still need to check the return value of these MS functions to make sure they actually succeeded. Don't assume.
Let's shift to building higher quality C. Organization matters. The book talks about breaking programs into components, aiming for low coupling and high cohesion. Can you unpack those?
Sure. Low coupling means components should be as independent as possible. Changes inside one shouldn't ripple uncontrollably through others. High cohesion means the stuff inside a single component should be strongly related, focused on a single purpose.
Can you give an example of high cohesion from the standard library?
String is a perfect example. Everything in there, strlen, strivalion, deals only with null-terminated strings. It doesn't mix in file operations or math. That focus is high cohesion.
And this leads to data abstractions and using libraries. The idea is separating the public interface, what users see in the header file, from the hidden implementation details in the source file. Why is that so valuable?
Maintainability and flexibility. It lets you change how a component works internally. Maybe you found a faster algorithm without breaking the code that uses it. As long as the public interface, function names, parameters, types in the header, stays the same, the users don't care about the internal rewrite.
And libraries, like the C standard library, are just prepackaged components using this principle.
It's exactly. Reusable, tested code that hides its implementation details behind a stable interface.
We also need to understand linkage when working with multiple source files, how identifiers are shared or not shared.
Right. There's internal linkage, static keyword visible only within that one.c file.
Yeah.
External linkage, visible across files. The default for global functions variables, unless static. And no linkage, like local variables.
Okay. Tools and techniques for robustness. Assertions, catching errors early.
C11 gave a static assert. This happens at compile time. You give it a constant Boolean expression and a message. If the expression is false, compilation stops with your message.
Great for checking assumptions developers make, like size of ponchit being 4.
Exactly. Or ensuring an array size macro has a certain value. Catches bugs before the code even runs.
And then there's the runtime assert macro from assert.h.
Yep. Takes an expression. If it's false at runtime, the program aborts, usually printing the failed expression, file name, line number. Super useful for debugging.
But the book stresses, use assert only for programming errors, right? Not for expected runtime issues.
Absolutely critical distinction. Assert checks things that should never happen if the code logic is correct. Preconditions, postconditions, invariants. Things like invalid user input or running out of memory, those are anticipated runtime conditions. You need proper if checks, Error handling, return codes for those, don't use assert for them.
And speaking of catching errors, the compiler itself is a key tool.
Your best friend if you listen to it.
The advice is never ignore compiler warnings. Fix the code.
Please, don't just suppress them. Warnings often point to real bugs, potential undefined behavior, or portability issues. Treat warnings as errors during development. Clean code compiles without warnings.
Let's talk compiler flags. There are some real game changers for quality and security. For GCC and Clang, -defortify source 2. What does that do?
It enables extra runtime checks and library functions like mempy and sprintf to detect some buffer overflows, basically making them safer if the compiler can determine buffer sizes.
And -base WLPy for ASLR.
Yes, that combination builds position-independent executables. It allows the operating system's address space layout randomization, ASLR, to be much more effective.
Can you remind us what ASLR does?
ASLR randomizes the memory addresses where key parts of a program, the executable code, libraries, stack, heap, are loaded each time it runs. This makes it way harder for attackers to predict memory locations needed for exploits, like jumping to specific functions or overwriting specific data. It's a core security defense.
Okay, other essential GCC Clang flags.
Notice G3 for maximum debugging info, NAJ02 for good optimization, WAL to enable most recommended warnings, WERR to treat those warnings as error, NAJA TCDC17 to specify the C standard version, and NAPedantic for stricter standard conformance warnings.
And for developers using Microsoft's Visual C++ Think, what are the equivalents?
Similar goals. Guard.cf enables control flow guard, another exploit mitigation technique. Analyze runs their static analysis tool during compilation. SDL enables security development lifecycle checks, adding more warnings and security features. Permissive enforces stricter C++ standard conformance, which also helps with C. Then O2 for optimization. W4 is a good warning level, similar to NakeWall. Don't use WAL in MSVC, it's too noisy. And WX treats warnings as errors.
Using these flags consistently seems crucial for professional C development.
It's night and day. They catch so many potential problems early.
Beyond the compiler, we have debugging and testing. Debuggers, GDB, Visual Studio Debugger, let you step through code, inspect variables, needs that SG or Z flag. And unit testing frameworks like Google Test help automate check and code behavior.
Yeah, writing tests that verify functions, produce expected outputs, handle edge cases correctly.
But the book cautions, passing tests doesn't mean defect-free code.
No, tests only check what you think to check. They can miss subtle interactions or edge cases.
Which is where static analysis really shines.
Exactly. Static analysis tools scan your source code without running it. They perform deep analysis, looking for patterns of potential bugs, possible null pointer dereferences, resource leaks, uninitialized variables, complex logic errors, security vulnerabilities. They can find things that are really hard to trigger reliably through testing.
And finding these bugs before deployment is way cheaper.
Orders of magnitude cheaper. Think Visual C++ Analyze, the Clang Static Analyzer, commercial tools like Code Sonar, SonarQube, Coverity. They're invaluable for serious C projects.
Wow. Okay, so we've journeyed pretty deep into effective C. We've seen the details matter, from basic puts error checks to the nuances of pointers and unsigned integers, the dangers of gets, the importance of structure, and the power of modern tools and compiler flags. C demands respect, demands understanding.
It really does. It might seem complex, maybe even dated to some, but that closeness to the hardware, that control, that performance, that's why it's still so fundamental. It really does underpin so much of our computing world, like the book says, strengthening that foundation.
Which brings us to a final thought for you, the listener, to consider. Given how foundational C is, and given all these subtle, powerful behaviors we've discussed, how much more secure, how much more reliable could our digital world actually be? If every C programmer truly adopted this effective mindset, deep understanding, rigorous checks, relentless pursuit of correctness, what systems are out there right now just waiting for that level of mastery?